Welcome. Hi, I'm Shanda Craft, and today we're exploring iridium, one of the rarest and most remarkable metals on Earth. What is iridium? Iridium is a platinum group metal, PGM, known for its extreme corrosion resistance, high density, and the second highest melting point of any element at over 2,446 degrees Celsius. It's not mined directly, but recovered as a byproduct from nickel or platinum ores, mainly in South Africa and Russia. Due to its properties, iridium is vital in high temperature and harsh environment applications. In this video, we'll focus on its complex manufacturing processes from extraction to purification and forming, and highlight specific finished products. Iridium processing is challenging because of its high melting point and chemical inertness. It involves multi-stage refining from ores or recycled sources like spent catalysts, electronics, or spark plugs. Iridium is considered the most corrosion-resistant metal known due to its extremely low chemical reactivity, surviving hot aqua regia acids and oxidation up to very high temperatures. Its inertness stems from a high electron configuration stability, low reactivity, and high cohesive energy. It only reacts with oxygen or fluorine at temperatures above 600 degrees Celsius. First, extraction and pretreatment. Raw materials, often nickel mining residues or industrial waste, undergo physical separation using gravity, magnetism, or flotation to concentrate the platinum group metals, including iridium. The ore is then roasted or smelted at high temperatures to oxidize and separate impurities. Next comes chemical refining. The concentrated material is now dissolved in aqua regia, a powerful mixture of nitric acid and hydrochloric acid. Remember, aqua regia does not dissolve the iridium. This dissolves many other metals, forming soluble compounds like chloruridic acid, also known as chloruric acid, hydrogen hexachloridate 4. It is a brownish-black chloride-based salt of iridium in the 4+ oxidation state. It is primarily used as a precursor for other iridium compounds and to create stable electrodes for the chloralkali process, usually available in high purity or technical grades. The solution is evaporated and iridium precipitates out. Purification is critical for high-quality iridium. Modern methods use solvent extraction or ion exchange to separate iridium from other platinum group metals like rhodium or platinum. The purified compound is then reduced, heated in hydrogen gas to reduce iridium sponge or powder at 99.9% purity or higher. For ultra-high purity needed in electronics, advanced molecular separation techniques are used. The biggest challenge is melting and forming due to the 2,446 degrees Celsius melting point. Standard furnaces can't handle it, so specialized methods are required. Plasma melting furnaces use ultra-hot plasma arcs exceeding 5,000 degrees Celsius to melt iridium while vaporizing residual impurities. Companies like Furuya Metal use double plasma melting for high purity ingots. Even more advanced is electron beam melting. Here, a focused electron beam in a vacuum melts the material, reaching localized temperatures high enough for further purification by evaporating volatile impurities like iron, aluminum, and silicon. Electron beam melting can remove many trace elements, including producing iridium with exceptional purity from 99.95% to 99.998% for critical applications. The process is highly effective at removing volatile impurities such as aluminum and iron via vaporization in a vacuum, making it suitable for creating high purity, low impurity iridium ingots and targets. After melting, ingots are processed through hot forging, rolling, or extrusion at temperatures from 1100 to 1700 degrees Celsius to form sheets, wires, or shapes. Precise temperature control prevents cracking as iridium is brittle at lower temperatures. Recycling is increasingly important, up to 99% from scrap using similar, up to 99% recovery from scrap using similar chemical and melting steps reduces reliance on mining. Now let's look at specific finished products that rely on iridium's durability. One key product is high-performance spark plug electrodes. Iridium's corrosion resistance and hardness make it ideal for center electrodes in automotive and aviation spark plugs. These last up to 25% longer than conventional ones, improving efficiency and engine life. Wire filaments and iridium wires are used in lighting in steel factories because they don't melt at the same temperatures that the steel melts. One major example of a product made from iridium is the crucibles for growing sapphire crystals in the electronics industry. Iridium crucibles withstand extreme heat without contaminating or corroding. This is essential for producing high-quality sapphire used in light-emitting diodes, LED lights, semiconductors, and high-performance electronics. Iridium is also used in industrial catalysts like electrodes in chlor-alkali processes for chlorine production and increasingly in proton exchange membranes, PEM electrolyzers for green hydrogen production, where its stability in acidic conditions is unmatched. However, due to its extreme rarity, which is 40 times rarer than gold, and high cost, current iridium demand poses a major bottleneck for scaling up green hydrogen production to gigawatt levels. In summary, iridium's manufacturing involves complex refining with chemical dissolution in aqua regia, purification through solvent extraction and reduction, and specialized high-temperature melting like plasma arc melting and electron beam melting, enabling its use in demanding finished products like crucibles for electronics crystal growth and durable spark plugs. As demand grows for green technologies and advanced electronics, efficient processing and recycling will be key to its future. Thank you for watching. This presentation was created with assistance from Grok, built by XAI. Thank you to Grok for helping compile factual details and structure to the content.